Hi everyone and welcome back. In this video, we are going to solve the lead code problem, special positions in a binary matrix. We are given n by n binary matrix and we need to return the number of special positions in this matrix. A position I and j is called special if at this position it equals 1 and all other elements in row I and column j are zeros. So we are given a binary matrix, meaning that it contains only zeros and ones. A position at row I and column j is called special if three conditions are true. First, the value at that position is 1. Second, row I contain exactly a single one. And the third condition is column j also contain exactly a single one. Our goal is to count how many such a special position exist in the matrix. A brute force or a naive approach here would be to check for everyone in the matrix and whether the rest of its row and column contain only zeros. But that would require repeatedly scanning rows and columns, which is inefficient. Instead, we can optimize this by separating the problem into two phases. The first one, we count how many ones exist in each row and each column. Second, we scan the matrix again and check which one satisfy the special condition. This allows us to make every check in a constant time. So let's take an example here and walk through it. Suppose we have a matrix look like this one. It has 1, 0, 0, 0, 0, 1, and 1, 0, 0. First, we count the number of ones in each row. So at row 0, we have a single one. Let's name it row 0. And at row 1, we have a single one. And at row 2, we also have a single one. Next, we count the number of ones in each column. So in column 1, we have 2 ones. In column 2, we have 0 ones. And in column 3, we have a single one. Now we check each position that contains a 1. So we'll check this position, and this position. You will find out that the cell at row 1 and column 2 is the only one that satisfies the condition, because at row 1 we have single one, at column 3 we have a single one. So the final answer is we have only a single special position. So the final answer is 1. Now let's go through the code that implements this idea. We will start first by storing the number of rows and columns in the matrix. So let's define two variables. Let's name it int rows equal matrix size. another variable called columns, called the column size. Then we will create two helper array. One array store the number of ones in each row, and the other one store the number of ones in each column. So let's define two vectors. Let's name row count. It has a size of rows and initial zeros. And the same, we will have another array column count that has the size of columns and initially zeros. Next, we will loop through every cell in the matrix, and whenever we encounter a 1, we increment the corresponding row counter and column counter. So we will loop on the matrix r less than rows plus for j equal 0, j less than columns plus j. Then we will check if that position matrix I on j equal 1, and if so, I'll increment the corresponding position, row and count positions by 1. So after this step, we know exactly how many ones exist in every row and column. Now we scan the matrix one more time, and for each cell, we check the three conditions. As you remember, the first one, if the cell value is 1 or not, then the count of ones in its row must be exactly 1, and the count of ones in its column must be also exactly 1. So let's first define a variable called result to hold the final result. Then we will loop again. I'll copy that loop to save some time. Again, I loop in on each element in the matrix, but at this time, I'll check if the position has 1 and if the row count at the row position also equal 1, and finally if the column count equal 1, and if yes, I'll increment my result variables. So if all the three are true, we increment our result variable, and after checking all the cell, we return the total number of special position. So after this loop, I'll return the result. Let's now run it to make sure it's error-free. Yes, and all the test cases pass. Let's submit it. And as you can see, in terms of complexity, we scan the matrix twice, so the time complexity is O of, let's say, R multiplied by C, where O of R multiplied by C, where R is the rows and C the columns. And for the space complexity, we use an extra space here. So the space complexity will be O of R plus C, which is efficient and optimal for this problem. So this is my explanation for today's problem. Thanks for watching. If you found this explanation helpful, please like and subscribe, and I'll see you in next problem. Bye.